Welcome back to an introduction to real analysis. Continuing through this text section by section, we're now in chapter 2, section 3, the limit superior, limit inferior, and the Bolzano Weierstrass theorem. What are we going to be doing in this section? Primarily, we will be looking at bounded sequences and certain subsequences of them. In particular, we're going to define the limit superior and limit inferior, generally just called Limsup and Liminf, of bounded sequences. We're then going to prove something called the Bolzano Weierstrass theorem for real-valued sequences, which will be an indispensable tool for us, which will show the existence of certain convergent subsequences. Now, earlier we proved that every convergent sequence is bounded, but we did see that there are many ways you can have bounded sequences which do not converge. For example, the alternating sequence of plus or minus 1 is bounded, but does not converge. However, we will still be able to compute certain limits within bounded divergent sequences of subsequences. So first, let's talk about upper and lower limits. There are ways of creating monotone sequences out of any sequence, and in this fashion we're going to get what are called limsups and liminfs, or limit superior and limit inferior. These will always exist for bounded sequences. So first, suppose you have a sequence xn which is bounded. In other words, the set of values that the sequence takes is bounded. So any subset of that will automatically bounded, meaning every tail is also unbounded. We can therefore take the sup and inf of every tail. If the sequence is bounded, so is every tail. Therefore, every tail has a sup and an inf. So this leads to definition 2.3.1. Suppose xn is a bounded sequence. Denote an and bn to be the sup and inf of the tails. So a sub n is the sup of the n tail, and b sub n is the inf of the n tail. Now, we can call the lim sup to be the limit of the ans, and the lim inf to be the limit of the bn's. Well, let's talk about this for a moment. For a bounded sequence, the lim inf and lim sup will always exist. We will prove this quite shortly. It is possible to define a liminf and limsup for unbounded sequences if we allow plus and minus infinity, and we will do that later, but for now we're only talking about bounded sequences. It's not that hard to generalize the results to include unbounded sequences. We're going to have a bunch of results, and if you just sort of think what would they imply for unbounded sequences, it all basically makes sense, but for now, just bounded sequences. Prop 2.3.2. Suppose xn is a bounded sequence, an and bn are the sup and inf of the n tails, then the sequence of sups of n tails is bounded and decreasing, and the sequence of infs is bounded and increasing. In particular, the lims inf and lim sup always exist. This justifies our definition of the lim sup and lim inf. These limits always exist. In particular, the lim sup of the sequence is the infimum of the sups of tails, and the lim inf of xn is the supremum of the infs of tails. We also obtain the inequality that the lim inf of a sequence is always less than or equal to the lim sup. So can we prove all of these things? If an, the sequence of sups of n tails, if it is bounded and decreasing by the monotone convergence theorem, it will have a limit. So if we can show that the ans are bounded and decreasing, we're good. Similarly, if the bn's are bounded and increasing, then the lim inf will exist. So the monotone convergence theorem also tells us that if the ans are bounded and decreasing, then their limit is their infimum. Similarly, if the bn's are bounded and increasing, then their limit is their supremum. That is the second bullet point of Prop 2.3.2. It really follows directly from the first, thanks to the monotone convergence theorem. Okay, let's show that the ans are monotone decreasing. So the an is the sup of the n tail. an plus 1 is the sup of the n plus 1 tail. But the n plus 1 tail is a subset of the n tail. Since it is a subset, the supremum can only be lesser. It cannot be larger. In other words, an plus 1 is less than or equal to an. So the ans are monotone decreasing. An identical proof will show you that the bn's are monotone increasing. They are infs of tails, which are subsets of one another, and the infs can only go up. But we also have the following. The inf of a tail is less than or equal to the sup of a tail. Therefore, bn is always less than or equal to an. So the bn's are getting larger, the an's are getting smaller, but we always have this inequality between them. So we can chain all of these inequalities like so. b1 less than or equal to b2 and so forth all the way up to bn, less than or equal to an, and so forth all the way to a1. So not only are the an's decreasing, but they are bounded below by any particular bi, and the bn's are not just increasing, but bounded above by any particular ai. Therefore, each of these sequences are monotone and bounded. This means we have established the first two bullet points. Let's move on to the third, that the liminf and limsup don't just exist, but the liminf must be less than or equal to the limsup. Now, we've already seen that an is always bigger than or equal to bn. So recalling this old lemma, 2.2.3, since they have limits and an is always bigger than or equal to bn, the limit of an must be bigger than or equal to the limit of bn. In other words, the limsup is bigger than or equal to the liminf. Let's visualize what we've been doing here. Okay, so here we have a particular sequence marked with dots. Here they all are, all of our xn's. Let's mark the sup of a tail with red circles. So what happened here? If I only look at the entire sequence, here is the sup because this value was taken here. In fact, all of the tails up to that point will see this as a supremum. But once I exclude this term, it appears that this is now the largest thing we will see. So the next two tails will have this as their supremum. But once this value is excluded, I now see a different largest value. As we move on, our sups can only go down. What about our infs? They can only go up as we start looking at successive tails. So the sups are a monotone decreasing sequence, the infs are a monotone increasing sequence, and they bound one another. Let's look at example 2.3.3. Suppose we have a sequence defined by 1 plus 1 over n when n is odd, or just 0 when n is even. Then we claim the limsup is 1 and the liminf is 0. All right, let's get proving. Every tail is certainly bounded below by 0 because every other term is 0 and the other ones are 1 plus something. So no tail is bounded below by a positive number because every other term is 0. Okay, so the inf of every tail is definitely 0. Therefore, the limit of those infs, the limit of the bn's, will simply be 0. The odd index terms are decreasing. Okay, if we have 1 plus 1 over n and we let n get bigger, we can only get smaller. So the odd index terms are decreasing, but they are all positive. So the sup of any tail will be the first odd index term. The even index ones are all 0. The odd index ones are positive and decreasing. So the supremum will simply be the first odd index term that we see. So if n is odd, the sup is simply the first term. If n is even, it's the next term. So the sequence of supremums is given by 2, 4/3, 4/3, 6/5, 6/5, 8/7, 8/7. Note that when n is even, you simply take the next term, and then you move to n is odd, where you take that term again. So you keep seeing the same thing twice. So as an exercise, simply establish that this has limit 1. It's not a terribly difficult exercise, but it does take a little bit of doing. So therefore, we also observe this sequence doesn't converge. Okay, every other term is very close to 1, and every other term is exactly equal to 0. So one may show that this sequence does not converge. We will have a general result to this effect in just a moment. So theorem 2.3.4, if you have a bounded sequence, there exists a subsequence converging to the limsup, and there also exists a subsequence, probably a different one, converging to the liminf. Let's prove it. We're only going to do half of it. We're going to prove the existence of a subsequence converging to the limsup. It's totally analogous to construct a sequence converging to the liminf. So as we've been doing, denote by an the supremum of the n tail. And denote limit of these supremums of n tails to be the limsup, and we're just going to call that x for convenience. We're going to construct the indices of our subsequence inductively. First, just begin with n1 equals 1. Just start somewhere, pick the first term of the sequence. Now let's inductively assume that you have chosen a bunch of terms of this subsequence. So an, recall, is the sup of the n tail, and they are converging to x. So, assuming we've picked a bunch of terms of our subsequence, which we hope converges to x, consider the tail given by starting just past where you previously cut yourself off. So having just picked x sub n sub k minus 1 as a term of your subsequence, cut out everything up to that term and look at the tail after this point. The tail has a supremum, and in fact it is a sub nk minus 1 plus 1 because that is the first index that we see here in the tail. So this quantity, this term of the sequence minus 1 over k, isn't an upper bound on the tail because it's less than the sup. It's the sup minus something. If it's not an upper bound, there is something in the tail bigger than that. Something in the tail is bigger than this number that is not an upper bound. Whatever that index is, which is inside this tail, and therefore the index has to be bigger than nk minus 1, pick that to be n sub k. So an is the sup of the n tail. We know that they are converging to x, and we have inductively constructed a subsequence so that xnk is always larger than a certain sup minus 1 over k. But the an's aren't just converging to x, they are decreasing. Also, this index is definitely bigger than or equal to this one, which is bigger than nk minus 1. So just to sort of simplify things a little bit, we can say xnk is bigger than ank minus 1 over k. If this is bigger than a thing minus something, and I simply make that even smaller by increasing this to make this subscript larger, because remember the an's are decreasing. So if I replace this index with a larger one, I've only made it smaller. This inequality still holds, and this is just an easier thing to look at than all of these plus or minus ones floating about. So here's what we have. We have constructed our subsequence, and xnk is always bigger than that. But ank is the supremum of the nk tail, so xnk must be less than or equal to ank. Now we have this squeezing going on. And if we throw the squeeze lemma in here by letting k go to infinity, this is a subsequence of the a's. The a's are converging to the limsup, so this subsequence converges to the limsup. This converges to the limsup, and this converges to 0. So both of these are converging to the limsup by the squeeze lemma. Therefore, this subsequence is converging to the limsup, which is all we needed to do. How can we use liminf and limsup productively? So the advantage to liminf and limsup, while they are a little bit abstract to get your head around at first, is that for any bounded sequence, they must exist. If we could somehow compute them, you can also compute the limit, or show that there isn't one. Working with liminf and limsup is sort of like working with limits, but there are some differences. Prop 2.3.5. Suppose you have a sequence which is bounded. The limit exists if and only if the liminf and limsup are equal to one another. In which case, whatever that shared value is, that is the limit of the sequence. Can we prove it? Let an and bn be the sup and inf of the n-tails as we have been using. In particular, for any particular term of the sequence, the sup of the n-tail is bigger than or equal to something belonging to the n-tail is bigger than or equal to the inf of the n-tail. So the squeeze lemma immediately gives one direction of this proof. In other words, if an and bn are converging to the same thing, xn must be converging to that thing as well. Now let's suppose the sequence does converge. We need to show that the liminf equals the limsup, which is equal to this limit. So there must be a subsequence converging to the limsup. However, the original sequence converged to x, so every subsequence must converge to x. So this subsequence converging to the Limsup must converge to x. And similarly, the subsequence that converges to the Liminf must be converging to x, so this x, whatever the limit is, must be equal to the Liminf and the Limsup. Prop 2.3.6. Suppose you have a bounded sequence and a subsequence. Then you can establish the following inequalities. The liminf of the original sequence is less than or equal to the liminf of the subsequence. The liminf of the subsequence is less than or equal to the limsup of the subsequence, and the limsup of the subsequence is less than or equal to the limsup of the original sequence. How can we prove this? Well, the middle inequality, that the liminf of the subsequence is less than or equal to the limsup of the subsequence, we've actually already shown. For any sequence, the liminf is less than or equal to the limsup. So this inequality is just prop 2.3.2. The left and right inequalities state that if you pass from a sequence to a subsequence, the liminf can only go up and the limsup can only go down. They are proved totally analogously. We are only going to prove the one regarding limsups. So, denote by AM the sup of the M tail of the original sequence, and by CM the M tail of the subsequence. Now we've established way back when first working with subsequences, that the index for your subsequence is at least as large as k. The kth choice of index must be at least as large as k itself. So if k is at least as large as m, then nk is also at least as large as m. In other words, what we're saying here is that the M tail of the subsequence is a subset of the M tail of the original. A subsequence keeps certain terms and throws some of them away. So if you take a tail of that, you are a subsequence of a tail of the original sequence. Therefore, the sup of this subset is less than or equal to the sup of this larger set. That's what this says right here. So the limit of the AM will be at least as large as the limit of the CN. That's all we needed to show. The limsup of the original sequence is bigger than or equal to the limsup of the subsequence. And again, the statement in prop 2.3.6 about liminfs passing to a subsequence proved exactly analogously. One corollary that we get out of prop 2.3.6 is the following. The limit superior and limit inferior, the limsup and liminf, are the largest and smallest values you can possibly have as limits of subsequences. Suppose you have a subsequence that has a limit. Then the limit of this subsequence must be the limsup and liminf of that subsequence. So any subsequence which converges will be converging to something between the liminf and limsup of the original sequence. Similarly, we get the following test for convergence of a bounded sequence, which we do not prove herein. It is left as an exercise. Prop 2.3.7, a bounded sequence converges with limit x if and only if every convergent subsequence also converges to x. Okay, let's move on to the big result of this section, the Bolzano Weierstrass theorem. Okay, so it's not true in general that a bounded sequence converges. We have counterexamples to that claim. But the Bolzano Weierstrass theorem is going to tell us we can find a convergent subsequence. So the version that we're going to present here is the Bolzano Weierstrass theorem for sequences of real numbers, but there is a more general result known as the Bolzano Weierstrass theorem that holds in more general circumstances. We'll discuss it very briefly. So here it is, the Bolzano Weierstrass theorem for real valued sequences. If a sequence is bounded, then there is a subsequence that is convergent. Okay, we can prove it pretty quickly actually. By theorem 2.3.4, there must be a subsequence that converges to the limsup. There, done. If the sequence is bounded, there is a subsequence converging to the limsup, so there's a subsequence that converges. So it actually appears that theorem 2.3.4 gives much more information than the Bolzano Weierstrass theorem. Bolzano Weierstrass just says there's a subsequence that converges. 2.3.4 tells us there is a subsequence converging specifically to the limsup and a subsequence converging to the liminf. So why has the Bolzano Weierstrass theorem got a name? That tends to imply it's more important. The Bolzano Weierstrass theorem is a more general result that holds in different circumstances, not just sequences of real numbers. So in this context, just porting over the statement of the Bolzano Weierstrass theorem, if a sequence is bounded, then it has a convergent subsequence, appears to lose some information. But in general circumstances, that statement is the more powerful one. Okay, we're going to give a second proof of the Bolzano Weierstrass theorem that hints towards the more general way to prove it. So we're going to construct two sequences, AI and BI, where AI is always less than BI. The AI are monotone increasing, the BI are monotone decreasing, and they have the same limit. Okay, then we're going to pick a subsequence that is squeezed in between them, and then we're going to throw the squeeze lemma at this. So if the first two bullet points are satisfied, okay, the AIs are always less than BI, but the AIs are increasing and the BIs are decreasing, then as we've seen in similar constructions, the AIs are not just increasing but bounded above by the Bs, and the BIs are not just decreasing but bounded below by the As. Therefore, they will have a limit by the monotone convergence theorem. Okay, so then, if the third and fourth bullet point hold, not only do they have limits, but the limits are the same, then I can throw the squeeze lemma at this and get this subsequence converging to something. Okay, xn is bounded, so we're going to pick a1 and b1 to be any lower and upper bound of the sequence. It doesn't really matter what they are, just real numbers that act as lower and upper bounds. Okay, and we're going to call d the distance between these numbers. If d is 0, if I can pick the same number to be an upper and lower bound, the only way that happens is if the sequence is constant and therefore it definitely converges. So let's go ahead and assume that d is positive. Then I'm just going to start an inductive procedure, and I have to start it somehow. Pick the first term of your subsequence by just picking the first term of the sequence. And observe, because a1 and b1 were our lower and upper bounds of the sequence, we definitely get this inequality that we wanted. So now look at the interval from a1 to b1. This contains every term of the sequence because we picked a lower and upper bound. Pick m to be the midpoint. I now have two different intervals whose union makes up the whole thing. At least one of them has to contain infinitely many terms of the sequence. Between the two intervals, I have to account for all terms of the sequence, and there are infinitely many. So how many terms of the sequence are in this interval, and how many are in this one? Possibly both infinite, but at least one of them is infinite. They cannot both be finite. If a1 to m has infinitely many terms, then I make the left endpoint, a, stay the same, and I take this midpoint to be the next b, in which case observe that the AIs are monotone increasing, they remained equal, and the BIs are monotone decreasing. I went from b1 to that midpoint to be equal to b2. On the other hand, if this interval does not have infinitely many terms, then the other one must. So set the midpoint to be a2, in which case the A's increased while the B's stayed the same. So here's a visualization of what's going on. Okay, our sequence is bounded, so we picked a lower bound and an upper bound without being particularly careful about it, and we just picked the first term of the sequence. Now, this contains infinitely many terms of the sequence. It contains all of them. So cleave the interval in half with a midpoint. At least one of these two pieces has infinitely many. Suppose it's the one on the left. Then I make this a2 and I make this b2. This has infinitely many terms of the sequence, so it has at least one. Pick x sub n sub 2 to be one of them. Doesn't particularly matter. Now what you do is you throw away all terms of the sequence whose index is up to n sub 2. But n sub 2 is a finite number. So what remains are infinitely many terms of the sequence, and specifically infinitely many terms in here. I started with infinitely many terms in here, and I threw away finitely many terms just up to that index. So that's the key to the inductive procedure. Okay, every time you have an interval, it contains infinitely many terms. So you have infinitely many terms whose index is bigger than whatever you want. Then you pick x sub n sub I to be something in that interval. Then you cleave it in half, ask which half contains infinitely many, and repeat. So we have satisfied all of our bullet points. The left endpoint of our interval is always less than the right. The left endpoints can only go up. They might stay the same, but they don't go down. The right endpoints might stay the same or they go down, but they definitely don't increase. Okay, this is the one we still need to satisfy. Okay, and also we have been picking our subsequence to be in the intervals that we're constructing. This is the only bullet point, this third one, that we need to look at. Okay, but at each stage, we cut our interval in half. So the length of the interval at one stage is half the length of the interval at the previous stage. It therefore follows that the ith interval is of length, the original starting length, over this growing power of 2. Okay, so the AIs have to converge, the BIs have to converge because they are monotone and bounded. Also, the distance between them is now seen to be going to 0, so they must be converging to each other, completing this proof of the Bolzano Weierstrass theorem. So let's talk a little bit, at least, about the more general formulation of the Bolzano Weierstrass theorem and how one might think to prove it. So suppose you have a bounded sequence. Now off to the right, I've drawn a collection of points in three-dimensional space. The Bolzano Weierstrass theorem is more general than just sequences in real space. But I had to draw something, so there they are, a collection of points in R3. But if it's a bounded sequence, what that means is there's a nice bounded volume that encompasses everything. So this sphere of finite radius includes every term of the sequence. We're now going to do a very similar inductive procedure. First, pick something. Just start your procedure somehow. Pick a term of the sequence. Now, cut your bounded region in half. You have two pieces. One of them must contain infinitely many elements. From that region, pick a new term, cut it in half, and continue. You have to do this technical thing of throwing away all terms whose index is up to a certain point just to make sure you're constructing a valid subsequence, but that's not really the point. The point is you continue to cut things into volume 1/2 of what they used to have. You have to be a little bit more careful than just doing that, but that's the basic idea. All right, let's extend this discussion of limsups and liminfs to include plus or minus infinity. So just as for ints and sups of sets, it's totally possible to allow certain limits to be plus or minus infinity. So how can we formalize this notion? Definition 2.3.9, we say that the sequence xn diverges to infinity if for every real number there is a cutoff point past which the terms of the sequence are bigger than that k. In this case, we say that the limit is infinity. If you can get all of this, but replacing this with a less than, you say the limit goes to minus infinity. So just to talk through again, if no matter what real number you pick, past a certain point, every term of the sequence is bigger than that, that's what you mean by going to infinity. If no matter what you pick, past a certain point, every term is less than that, that's what you mean by going to minus infinity. All right, proposition 2.3.10, suppose you have a sequence that's monotone but not bounded. Then the limit is either plus or minus infinity depending on whether it is increasing or decreasing. The proof really just boils down to this definition we just introduced about how we can state a sequence goes to infinity or minus infinity. So we're only going to consider the situation of an increasing unbounded sequence. As typically happens, the other half is totally analogous. So according to our definition, we need to do something for every k in the reals, so pick an arbitrary k. Since the sequence is increasing, it is bounded below by its first term. But the sequence is not bounded, so it is not bounded above. Okay? If the sequence was assumed to not be bounded, but we know it's bounded below, it must be unbounded above. Therefore, k is not an upper bound. This k that we picked is not an upper bound, so there is some term of the sequence bigger than that. But now, since the sequence was assumed to be increasing, every term past that point is bigger than k. And that's exactly what we had to accomplish in definition 2.3.9. We found an index past which every term is larger than k, and we were able to do this for any real number k. Let's look at example 2.3.11. The limit as n goes to infinity of n is infinite. The limit as n goes to infinity of n squared is also infinity, but the limit of minus n is minus infinity. The proofs are left as an exercise. They're not terribly difficult. Just work through that original definition. Also see proposition 2.3.10 for sort of a guide. How do these infinite limits interact with Limsup and Liminf? So we can allow Liminf and Limsup to take on the values infinity and minus infinity. Remember that Liminf and Limsup were defined as these limits. Unfortunately, the ANs and BNs from the definition of Limsup and Liminf, the sup and inf of the tails, might not be real numbers, but they might be extended real numbers. In particular, the sup of a tail might be infinity, or the inf of a tail might be minus infinity. So we don't yet have a functional working definition for how to take a limit of a sequence that might involve some extended reals. However, the extended reals are still ordered. Remember that infinity is bigger than every real number, and every real number is bigger than minus infinity. There's still an ordering. So you can take sups and infs. Which brings us to this definition. Suppose you have xn, a sequence of real numbers. As we've been doing, let an be a sequence of sups of tails, and bn be a sequence of infs of tails. We can simply define the lim_sup to be the infimum of the sups of tails, and the lim_inf to be the sup of the infs of tails. So prop 2.3.13, if you have a sequence that is unbounded above, the lim_sup is automatically plus infinity. If it is bounded above, then definition 2.3.12 agrees with the one back at the beginning, 2.3.1. We have two working definitions for lim_sup. For a bounded sequence, we will show that they are actually the same. For an unbounded sequence, this new definition gives us a plus infinity, whereas the old definition didn't give us anything. Similarly, if you have a sequence unbounded below, the lim_inf is minus infinity, whereas if it is bounded below, then the two definitions agree completely. Okay, let's get proven. We need to recall these definitions at right. If the sequence is unbounded above, as an exercise, show that every tail is also unbounded above. Well, if every tail is unbounded above, then the sup of every tail is plus infinity. So the set of sups of tails is just infinity. What's the infimum of that single element set? Infinity. So definition 2.3.12 tells us that since the set of sups of tails is just infinite, the inf of that set is just plus infinity. By definition 2.3.12, the lim_sup is infinity. Now let's suppose the sequence is bounded above. We want these two definitions at right to give us the same thing. However, we showed that when a sequence is bounded above, this lim_sup must exist because the ANs form a decreasing sequence. But by the monotone convergence theorem, if this is decreasing and bounded below, the limit is the infimum. That came from the monotone convergence theorem. So thanks to the monotone convergence theorem, these two definitions do agree when they both produce a result. So definition 2.3.12 does not overwrite in a bad way definition 2.3.1. It is completely consistent when bounded sequences are involved, but now gives us a way to talk about the lim_sup and lim_inf of unbounded sets as well. Okay, example 2.3.14. Let xn be 0 for odd indices or n for even indices. Okay, the sups are all plus infinity because this sequence is unbounded above. Every other term of even index is just getting bigger. So we have 0, 2, 0, 4, 0, 6, 0, 8. So the sequence is unbounded above, all of the sups are infinity. However, all of the infs are 0 because every other term is simply 0, and the other terms are positive. So the lim_inf is the sup of just a bunch of zeros. That's 0. The lim_sup, since it's unbounded above, is plus infinity. Because the lim_sup is not equal to the lim_inf, the limit does not exist. So let's go over everything we talked about in this section. For any sequence, the limsup and liminf are defined in terms of limits of sups and infs of tails. When the sequence was unbounded, we simply had a definition of what the liminf or limsup should be, but it is consistent. The definition really follows from previous definitions for bounded sequences, in which case these limits are real numbers, but there's a totally reasonable way to extend them to unbounded sequences using the extended real numbers in a way that is consistent with the definition for real numbers. The Bolzano Weierstrass theorem is kind of the big landmark theorem of this section. It tells us that any bounded sequence must have a subsequence that converges. It doesn't specifically tell us to what. We did have an earlier theorem that said any bounded sequence has a subsequence converging to its sup, and any bounded sequence has a subsequence converging to its inf. The Bolzano Weierstrass theorem just says any bounded sequence has a subsequence that converges to something. However, because it is a more general theorem that holds in more general contexts, it tends to be the one that in analysis we default to. So in the future, quite often when we have bounded sequences and we say, oh, therefore there is a subsequence that converges, we tend to just cite Bolzano Weierstrass and say converging to something. We don't just say converging to the sup or converging to the inf.